sometimes we know that a certain event A has occurred, right? Event A has occurred. That means I know that something here has happened, right? This designates event A. Now, this portion is what? A intersection B. A intersection B, right? And this is that part of A in which B has also occurred. This is that part of A in which B has also occurred. Now, if somebody says probability of occurrence of B, given that A has occurred, this designates probability of occurrence of B given that A has occurred. This means probability of B given that A has occurred. Probability of B given that A has occurred. If it was only about probability of B, then this would have been the set. But this time it's about probability of B given that A has occurred, right? That means occurrence of B subject to a condition. Occurrence of B subject to a condition. The condition is that A has occurred. Condition is that A has occurred. This is called conditional probability. This is called conditional probability. The probability of B given that A has occurred, is conditional probability. Probability of occurrence of B given that A has occurred is conditional probability. Very clearly then, for this probability, this is my sample space. This is my sample space. Do you realize that? This is my sample space. And this is the favorable region. This is the favorable region and this is my redefined sample space. This is my redefined sample space. Yes or no? Because A has occurred. So this then is my new sample space and this is my favorable region. Right? So which means probability of B given that A has occurred must be probability of A intersection B divided by probability of A. Probability of A intersection B divided by probability of A. Yes or no? Which means probability of A intersection B, probability of A and B occurring together could have been written as probability of A into probability of B given that A has occurred. On multiplying this with this, probability of A and B occurring together is probability of A into probability of B given that A has occurred. Yes or no? Okay, see, the probability of this portion will be proportional to probability of A intersection B, and this is my sample space, and this occurring will be like probability of A. Yes or no? This will be proportional to the total number of members in the sample space, and this would be the favorable region. This would be the favorable region, isn't it? Probability of B given that A has occurred, this designates my sample space, and this will be proportional to probability of A, right? Sample space will come in the denominator, and this will be my favorable region, and this occurring will be proportional to probability of A intersection B, isn't it? That's why. So probability of A and B is going to be probability of A into probability of B given that A has occurred. Probability of B given that A has occurred. Now, if A and B were independent events, see, if A and B were independent events, then probability of B given that A has occurred or probability of B, given that A has not occurred, will be the same as probability of B, isn't it? If A and B were independent events, if A and B were independent events, then probability of B, given that A has occurred, is the same as probability of B, because it does not depend on whether B has occurred or A has occurred or not. If A and B were independent events, probability of B, given that A has occurred, is the same as probability of B that A has not occurred, is the same as probability of B itself, right? Because A and B are independent events, in which case this will simply become PB, and then PA intersection B would be PA into PB for independent events, if A and B were independent events. It's quite a tricky affair to represent independent events on a Venn diagram. You would have to ponder over it. It's quite a tricky affair to represent independent events on a Venn diagram. It's not that simple. But nevertheless, if probability of A and B is probability of A into probability of B, then A and B are independent events. But in a general sense, even if they were not independent, this condition will still hold good. Probability of A and B would be probability of A into probability of B, given that A has occurred. Yes or no? That's a statement of what is called conditional probability. It's a statement of what is called conditional probability, right? Now, realize that PAB means probability of A given that B has occurred. Probability of A given that B has occurred. B has occurred. That means this has taken place. And then, what is the probability of A given that this region has occurred? Well, this becomes my new sample space. So this will be my denominator. Probability of B will be my denominator in this case, right? And this then would be my favorable region, which is probability, which will be proportional to A intersection B, right? That means another way to write probability of A intersection B is probability of A intersection B is probability of B into probability of A given that B has occurred. Given that B has occurred. This will be crucial. This will be crucial. That means probability of A intersection B could have been written in two ways. Probability of A into probability of B given that A has occurred, or probability of B into probability A given that B has occurred. Given that B has occurred. Both these statements are true. Both these statements are true. Consequence of what is called conditional probability. Conditional probability. Right? Now, suppose again, I roll a unbiased die. Right? I roll an unbiased die. Say A be an event of getting 4. A be an event of getting 4 when I roll the dice. And B be an event of getting more than 3. B be an event of getting more than 3. That means B would have elements 4, 5, 6. Right? Now, from very ordinary common sense, probability, if someone says probability of A, if someone says probability of A, given that B has occurred, probability of A given that B has occurred, that means this is my new sample space, and in which the probability of getting 4 would be 1/3, isn't it? Yes, very clearly 1/3, isn't it? Probability of A, given that B has occurred, this is B, in which the probability of getting A means 4 would be 1/3, because A has occurred. B is known to have occurred. So probability of A, that means this event, given that this event has occurred, is very clearly 1/3. Yes or no? But from the notation that we have learned, just my objective is to breed familiarity with notation. After I have given this notation to you, dump all the notation and we'll do probability bindas after that. But as of now, no, let's have this notation also in place. Okay. So probability of A, given that B has occurred, would be 1/3. Now from a notational perspective, probability of A, given that B has occurred, is probability of A intersection B divided by probability of B. Yes or no? Probability of A intersection B is like, now A intersection B has one element, which is 4. A intersection B has one element, which is 4. And the probability of getting that 4, that means A intersection B would be 1/6. Probability of A intersection B would be 1/6. That means getting 4 is 1/6. Now, probability of B, well, 3 out of 6. 3 out of 6. Probability of getting B is 3 out of 6, which is also 1/3. So that's from a notational perspective. From a notational perspective. Yes or no? Have this notation in place, because you will have to write things suitably in your board exams. So this notation is only for that far and no further, right? Now refer to the problem sheet. Problem number 5 of this problem sheet, where there is a matrix here. Male, female, employed, unemployed. This is 460, this is 140, this is 40, this is 260, right? Now, in this case, we need to find, so an employed person is selected at random. The problem says that an employed person is selected at random. That means I know this event has occurred. Selection of an employed person. Selection of an employed person. What is the probability that it's a male? What's the probability that it's a male? We want to find the probability of a male given that he is employed. Given that he is employed. Probability of male given that he is employed. Right? Now again, this becomes my new sample space, because I know that the person selected is employed. Person selected is employed. So this is my sample space, of which this is favorable, right? Of which this is favorable. So it's going to be 460 divided by 600. That's from common sense. That's from common sense. Now using notation. Using notation. Get that through too. Get that through too. Okay? Probability of getting a male given that he is employed, is probability of male intersection employment, male and employed, divided by probability that is employed. Yes or no? Now male and employed is like 460 divided by, this is 600 plus 300, 900, right? Probability of male and employed. How many members are there in male and employed? 460 divided by the total sample spaces. This is 600, 640 plus 260, 900. Yes or no? right? Male and employed. Probability employed would be 600 by 900. 600, this is 600 divided by total, which is 900. So this is 460 divided by 900 divided by 600 divided by 900, which is essentially the same thing. This is only for the sake of notation. This is only for the sake of notation. Otherwise, common sense. Use common sense. Right? Now, can I wipe this off? When you want to solve a good problem in probability, forget all notation. Otherwise, you'll get lost in the web of notation. You'll only think of notation. You'll not think of the problem. Same thing, same thing. So, it's okay to know notation. It's okay to know things a little formally, but it's also formally okay to unlearn these things when required to solve a problem, good problem, right? Now, so you understand conditional probability. You understand conditional probability, right? Now, suppose there is a big trunk. This is a trunk. This is a trunk. And there are 3 types of bags in this trunk. There are 3 types of bag in this trunk. Type A has 2 white balls and 3 red balls. And there are 3 bags of this type. There are 3 bags of type A. There are 3 bags of type A. And each bag containing 2 white and 3 red balls. Then there is type B. And say there are 2 bags of this type. There are 2 bags of this type. And this has 4 white balls and 6 red balls. It has 4 white balls and 6 red balls. And there are 2 bags of type B in this trunk. And then there is type C. And say there are 5 bags of type C. There are 5 bags of type C. And there are, say, 5 white balls and 2 red balls here. 5 white balls and 2 red balls. So type A, there are 3 types, and this is the constitution of all bags of type A. Type B, there are two bags of type B, and this is the constitution of type B bags. Similar type C bags, this is the constitution of type C bags. And they are 5 in numbers. Okay. Now, first let me do a common sense approach to this situation where I say I'm picking up a bag at random. I'm picking up a bag at random from the trunk. I'm picking up a bag at random from the trunk. And now from the bag that I have selected, I pick out 1 ball. What's the probability that it is white? You know what I'm trying to say? I pick up a bag at random. I pick up a bag at random. And then from that bag, I pick out a ball. What is the probability that it is white? You understand what I'm trying to say here? Okay. Now, probability that the ball selected is white. Okay. What are the various possibilities? Do you realize I could have picked up type A of the bag? What's the probability of selecting type A of the bag? 3 divided by 5, 5, 10, isn't it? The probability of selecting type A bag is 3 divided by 10. 3 divided by 10, right? That's type A bag selected with this probability. Now from this, the probability of selecting a white ball would be 2 by 5? Would be 2 by 5? Yes or no? Or means I'm going to add. I could have selected a type B bag, or I could have selected a type B bag. The probability of selecting a type B bag would be 2 by 10 and the probability of selecting a white ball would be 4 by 10. Or I could have selected a type C bag, or I could have selected a type C bag, and the probability of selecting a type C bag would be 5 by 10 into, then selecting a white ball would be 5 by 7. 5 by 7. Do you realize this is the probability of selecting a white ball? That's a total probability of selecting a white ball, yes or no? Do you understand this? Okay. Now let me formalize this for you. This is common sense, right? This is just common sense. It didn't require any formal treatment. But again, for the heck of it, let me give you a more formal treatment to this. Okay? Unnecessary but very necessary. Common sense will generally solve all the glitches. But again, let me formalize this issue. An issue of this kind, let me formalize. Suppose a sample space S is partitioned into events E1, E2, E3, En. These are the various events into which the sample space is partitioned, given that 1. Events are mutually exclusive. These events are mutually exclusive. That means no two of these events can occur simultaneously. That means EI intersection EJ is a null set. EI intersection EJ is a null set. Events are mutually exclusive. 1, 2. These events are exhaustive. These events are exhaustive. Exhaustive events. So, for example, in the earlier case, the events were picking type A of the bag, type B of the bag, type C of the bag. Right? Since I'm only picking one bag at a time, they are mutually exclusive. I'm not picking two bags at a time. Right? So no two of those events, picking up a bag of type A, picking a bag of type B, event E2, picking up a bag of type C, which is E3. These are three events. Do you realize they are mutually exclusive? They are mutually exclusive. And obviously they are exhaustive. They are exhaustive. Obviously they are exhaustive events, right? So these are, let's say, some events that are mutually exclusive and exhaustive. And they constitute the sample space. They constitute the sample space. They partition the sample space. So geometrically, if I have to represent these two facts, on a Venn notation, if I have to represent these two facts, This is my sample space S. This entire thing is my sample space S. Let me take a line. This partition is event E1. This region is event E1 of the sample space. This region is event E2 of the sample space. This event E3, this region is event E3 of the sample space, E4 of the sample space, En minus 1 of the sample space, En of the sample space. There is nothing common between any two regions. There is nothing common between any two of these n regions, so they are mutually exclusive. And together they constitute this entire sample space. E1 union E2 union E3 union En is the sample space S. Yes or no? So they are exhaustive events. They are exhaustive events. Yes or no? Sure, no? Now, each of these events could have resulted in another event A. Each of these events could have resulted in another event A. For example, in the earlier case, the three events were E1 drawing bag of type A, E2 drawing a bag of type B, E3 drawing a bag of type C. Now each of these events in turn could have resulted in drawing of a white ball. In drawing of a white ball, that's an event A. Right? Each of these events could have resulted in another event A. Another event A. Yes or no? E1 could have caused an event A, E2 could have caused an event A, E3 could have caused an event A, En could have caused another event A. In this case, for example, compare it with the illustration that I gave, that event A is drawing of a white ball. And each of the three bags represented by E1, E2, E3 could have resulted in drawing of a white ball. Yes or no? Right? So, this represents event A. This represents event A. This circle represents event A. And E1 could have caused A. This region represents A being caused by event E1. This represents the region event A caused by E3. Yes or no? This represents A intersection E1. This represents, A intersection E2. This represents A intersection E3. A intersection, this represents A intersection En. Yes or no? Now, if E1, E2, E3, En are mutually exclusive, then would you not want to believe that A intersection E1, A intersection E2, A intersection E3, A intersection E4 are also mutually exclusive events? Right? Yes or no? Right? A intersection E1, A intersection E2, A intersection En are mutually exclusive events? And any one of these events would have been the cause of A. Right? Any one of these events could have been the cause of A. Yes or no? That means, can I say that A is A intersection E1 union A intersection E2 union A intersection E3 union A intersection En? Can I not say this? Tell me. A is the union of all of this. These are, as far as A is concerned, these are exhaustive. This, they are exhaustive in as far as A is concerned. Together, they produce the entire A. Yes or no? Right? So far so good. Huh? That means probability of A, and see, since they are mutually exclusive, probability of this entire thing would be probability of this plus probability of this plus probability of this plus probability of this, because they are mutually exclusive, yes or no, right? So can I say probability of A is probability of A intersection E1 plus probability of A intersection E2 plus probability of A intersection En. Yes or no? Why? Because they are mutually exclusive. Yes or no? Right? This is like probability of drawing a white ball, which is like probability of a white ball from type A plus probability of drawing a white ball from type B plus probability of drawing a white ball from type C, and so on. So this is what it reduces to, so you can connect, right? It's not abstract. Now, from conditional probability that I just delivered to you a little while ago, this is like probability of E1 into probability of A given that E1 occurs plus probability of E2 into probability of A given that E2 occurs plus probability of En into probability of A given that En occurs. Yes or no? This was probability of drawing a bag of type A. What was that? Some 3 by 10? And then probability of drawing a white ball given that I've selected type A. Probability of drawing a type 2 bag, type B bag, which is E2, right? And then given that I've selected type B bag, what's the probability of drawing a white ball given that type E2 has been, type B has been selected? Do you realize that? This is only formalizing that fact. This is called total probability. And this is called total probability theorem. They call it total probability theorem. Right? In your exam, you'll have to write this way only. Please understand this. All right? So now, right? Well said, but let's maintain some restraint because we are in front of the camera, right? It probably will not do good. Yes or no? Right? Now, can I wipe this off? Look, let me go back to that original problem. The three types of bags. All right. Can you help me with the data? Type A, there were 3 bags, 2 white and 3 red. Then there were type B bags, 2 bags, 4 white and 6 red. And there were type C bags, 5, 2 red. All right. This was the constitution of the trunk. Now, now suppose I select a bag at random. I select a bag at random and I pick out a ball and I find that it is white. Please understand this. Select a bag at random. Select a bag at random. Pick a ball from that bag and it is found to be white. Found to be white. Right? I select a bag at random and then from the bag I randomly pick out a ball and I find that it is white. I know that this event has occurred. I know that this event has occurred. Now, what is the probability it came from type A? What is the probability that it came from type A? All right. We want to find the probability that it came from type A. That means this time I have knowledge of the event. It has known to have occurred. It has known to have occurred. And this event could have been because of very many causes. This could have been a cause of that event. This could have been the cause of that event. This could have been the cause of that event. Right? There are 3 different causes of that event. Now, I need to find the probability that of this being the cause. I want to find the probability of this being the cause. I want to find the probability of this being the cause. Right? The event is what? Occurrence of a white ball. And this event could have been triggered by any one of these 3 events. These could have been the causes of that event. These are the type A, type B, type C are the causes of that event. What's the probability that this was the cause? What's the probability that this was the cause? What's the probability that this was the cause? Yes or no? Yes or no? Now, say, picking up a type A bag is referred to as event A1, E1. Picking up of a type B bag, let me refer to this as event E2. Picking up of a type C bag, let me refer to that as E3. Yes or no? Then, what is probability of E1? Just picking up a type A bag, 3 by 10, right? What's the probability of E2? 2 by 10. What's the probability of E3? 5 by 10. These are the causes. E1, E2, E3 are the causes of what? Of an event A, of picking up a white ball, I want to find the probability that this is the cause. I want to find the probability that this is the cause. I want to find the probability that this is the cause. Right? Now, W is the event of drawing a white ball. Event of drawing a white ball. Event of drawing a white ball. Now I want to find, say, probability of E1 being the cause, probability of E1 given that white has occurred. This is what I want to find. Probability of E1 given that white has occurred. Yes or no? Probability of E1 being the cause, this bag being the cause, given the event white. Occurrence of a white ball. Event of drawing a white ball. Yes or no? Do you understand this? Acha, these probabilities, this is conditional, but these probabilities, I call them a priori probabilities. The This is before the final event. This is before the final event. Probability of drawing a bag of type A, probability of drawing a bag of type B, probability of drawing a bag of type C, right? These are the causes before the final event of drawing a white ball. These are called a priori probabilities. A priori probabilities, right? Now, I want to find the probability that E1 was the cause given that a white ball was drawn, right? Probability of E1 given that white has happened, white has been drawn, right? That from conditional probability is going to be probability of E1 and white, probability of E1 and white divided by probability of drawing a white ball. Probability of drawing a white ball, yes or no? Total probability of drawing a white ball, probability of E1 and white, yes or no? Then this from conditional probability is, so E1 into probability of white given that E1 was the cause, yes or no? E1 intersection W is going to be probability of E1 into probability of drawing a white given event E1. That means type A bag. Probability of drawing a type A bag, and then having drawn a type A bag, what's the probability of picking up a white ball? That's a numerator, right? Divided by, this is the total probability of drawing a white ball. This is the total probability of drawing a white ball, right? This from the total probability theorem is going to be, I could have drawn a type A bag into probability of white given E1, or I could have drawn a type B bag which is PE2 into probability of white given E2. I found this, that I called PA earlier, but now I'm calling PW, or probability of E3, probability of white given E3, yes or no? Do you all understand this? This would be the probability that E1 was the cause if a white ball was drawn. Okay. Now, what is PE1? These are PE1, PE2, PE3 are a priori probabilities. That has nothing to do with what ball was drawn. So, PE1, for example, is 3 by 10 into probability of drawing a white ball given that E1 has occurred is going to be 2 by 5. Is going to be 2 by 5 divided by PE1, which is 3 by 10 into 2 by 5 plus probability of E2 is going to be 2 by 10, and then drawing a white ball given that this has occurred is 4 by 10 plus probability of E3 5 by 10 into drawing a white ball given that E3 has occurred is going to be 5 by 7. This is going to be the probability that E1 was the cause if the drawn ball was white. Similarly, I can find E2W, denominator will be the same. If it was E2, the denominator remains the same, the numerator will become PE2, PWE2. This is what would happen, and so on and so forth. So this time, I have knowledge of the event of drawing a white ball. I'm trying to go backwards. I'm trying to find the probability of this being the cause, of this being the cause, and this being the cause. In earlier cases, what did I do? I had the causes in place and I wanted to find the probability of the event. Given the causes, I found the event. But now I have knowledge of the event. I'm going backwards. I'm trying to find the probability of the various causes that could have triggered the event. So in that context, I'm going backwards. And this essentially is what? This is only a statement of conditional probability. This essentially is only a statement of conditional probability. They have given it a name. They call it Bayes theorem. They call it Bayes theorem. They call it Bayes theorem or inverse probability. Inverse probability. They call it Bayes theorem or inverse probability. Right? To put it more in laymanish language, but so far so good, right? Not a problem. So you understand this notation, which you will have to duplicate, replicate in more formal, useless exams, right? Ayush, very serious? Good. Don't be that serious, otherwise the fun of probability will be lost. Let's always remain probable. Okay, can I wipe this off? Huh? So you know, there could have been a set of causes. Call them C1, C2, C3, Cn. Like were the bags, type A, type B, type C were the bags. There could have been these causes. And for each of these causes, there was an a priori probability. There was an a priori probability. Like for each of those bags, I had an a priori probability, PE1, PE2, PE3. I could have had, let's say, capital P1, capital P2, capital P3, capital Pn is the a priori probability. That has nothing to do with the event, final event. That has nothing to do with the final event. Each of these causes could have been instrumental in producing a certain event A. That means then there could have been a probability of an event A given the cause Ci, Now, that means if this was the cause, what was the probability of the event A? If this was the cause, C1 was the cause, what was the probability of A? If this was the cause, what was the probability of the event A? If this was the cause, what was, first the cause comes and then the event, right? So first this comes and now the event. If this was the cause, what was the probability of an event A being triggered by this cause? Because this cause by itself could have triggered several events, of which A is one. Could have triggered, right? In the earlier case, type A could have triggered two kinds of events, picking up a white ball and picking up a red ball, right? So each of these causes could have triggered several events, of which A is one. So there is a probability of A given the cause Ci. Right? Let me call it small p1, let me call it small p2, small p3, small pn. Yes or no? Now, probability of Ci being the cause given that A has occurred, the event A has occurred. Probability of Ci being the cause given that the event A has occurred, right? So this is some Ci which has an a priori probability Pi, and if this is the cause, the probability of the event is small pi. Then the required probability of Ci being the cause given that A has occurred is going to be Pi divided by P1 plus P2 Pn, Pn. This is the probability that Ci was the cause. Probability that C1 was the cause, this would become P1, P1, etc. Same denominator. Probability that C2 was the cause, this would become P2, P2, same denominator, and so on and so forth. This is the essence of inverse probability. This is the essence of inverse probability. Yes or no? Let me solve another problem for you. Let's take the sheet. But so far so good, right? Okay. Look at number 6, for example. So, India is playing Pakistan, Sri Lanka, and West Indies. Right? These could be looked upon as causes. Causes of a win. Causes of a win. Right? E1 is the event about playing Pakistan. E2 is the event about playing Sri Lanka. And E3 is the event about playing West Indies, isn't it? West Indies. No point playing Australia. Okay. And India plays 2 matches with Pakistan, 3 matches with Sri Lanka, and 5 matches with West Indies. Right? So now each of these events, each of these causes, Pakistan, Sri Lanka, West Indies, they have an a priori probability. They have an a priori probability, right? So the a priori probability is going to be, now for Pakistan, 2 by 10, 3 by 10, 5 by 10. That's the a priori probability of this, right? And then probability of winning. That is small pi's. These are capital Pi's. Now small pi. Against Pakistan, what's the probability of winning? 0.6. Against Sri Lanka, what's the probability of winning? 0.5. Against West Indies, 0.4. Now it's as if, you know, I pick up a draw and it's about India having won that match. What's the probability that that match was against Pakistan? I always wish it was very high. That probability was very high. So what's the probability that if India has won, it was against Pakistan? Very clearly. So I look at this. So it will be like this into this, divided by this into this, plus this into this, plus this into this. Right? Probability that Pakistan is the cause. Pakistan is the cause. Given that we have won, is going to be 0.2 into 0.6 divided by 0.2 into 0.6, 3 into 0.5, 0.5 into 0.4. Right? That's a probability. Now, again, for the sake of notation, bear with me. Probability PE1 is 0.2. A priori probabilities E2 0.3, E3 0.5, right? We need to find the so this is the event of winning. This is the event of winning. We want to find the probability of even being the cause given that we have won. Probability of even being the cause given that we have won is going to be probability of E1 into probability of win given E1 divided by probability of E1 into probability of win given E1 plus probability of E2, that means Sri Lanka, into probability that we win given we are playing Sri Lanka, plus probability E3 West Indies into probability of win, given that we are playing West Indies. Now, PE1 is going to be 0.2. Probability of win against Pakistan. Probability of win against Pakistan, that's 0.6. Right? So the numerator is 0.2 into 0.6, and the denominator again you can see 0.2 into 0.6 divided by 0.3 into 0.5 divided by 0.5 into 0.4. It's conditional probability, inverse probability. Yes or no? Right? Let me give you another illustration. But so far so good, right? Look at problem number 8. There is a bag that contains 3 math books and 2 physics books. There is this bag that contains 3 maths books and 2 physics books. Now, if a book is drawn at random from this bag, a book is drawn at random from this bag, and if it is maths, that means if the book drawn is a maths book, if the book drawn is a maths book, what is done is the original book plus 2 more maths books are replenished in this bag. The original book plus 2 more maths books are replenished. That means the original 3 plus 2 more maths books, that means 5 maths books and 2 physics books. That would be the new state of the bag. If a maths book is drawn from this bag, then the new state of the bag would be, 5 maths books and 2 physics books. 5 maths books and 2 physics books. The original maths book is placed back in the bag and 2 more maths books are added. So that would be the new state of the bag. If a physics book is drawn from the bag, if I draw a book randomly and if the book drawn is a physics book, it is not replaced in the bag. It is not replaced in the bag. That means the new state of the bag then is 3 maths book and 1 physics book. 3 maths book and 1 physics book. Now, this experiment is repeated 3 times. This experiment is repeated 3 times, right? 3 drawings are made. And if the third draw gives a math book, what is the probability that the first 2 drawn books were of physics? You know what I'm saying? In the third draw, a math book was obtained. What's the probability that in the first 2 draws, physics books were taken out, drawn out, right? Okay. Now, the first 2 draws can be classified. The first 2 draws it could be a maths. Both could be maths books. That's 1. 2. It could be a first maths, second physics. That could be a second event possible. Third event. Physics and then second draw maths. And the fourth event, physics. These are 4 possibilities. Yes or no? These are 4 possibilities. In the first 2 draws, right? In the first 2 draws, these are the 4 possibilities. Now, let me look at the a priori probability for each of these. Let me look at a priori. That means PI. Let me look at PI, the a priori probabilities for each of these 4 events, right? Now, maths in the first draw, is like 3 by 5. Yes or no? Is 3 by 5? And maths in the second draw. This is now 5 by 7. Maths in the second draw would be 5 by 7. 5 by 7. So that makes it 3 by 7. That's the a priori probability of this event, this cause. These are the 4 causes. These are the 4 causes. I want to find the probability of this being the cause. Right? I want to find the probability of this being the cause. That means the first 2 draws being physics. Yes or no? Okay. Now, maths in the first draw is 3 by 5. And physics in the... So, if maths is drawn in the... Then I come to this state. And then it's going to be 2 by 7 into 2 by 7. Physics 2 by 7. 6 by 35? Yes or no? Now, physics in the first draw is going to be 2 by 5. If physics is drawn in the first draw, then I come to this state. Then I come to, and then a maths is like 3 by 4. A maths is like 3 by 4. Physics and then maths. 3 by 4 maths, right, in the second draw. Which is 3 by 10. Right? For this case. Now, this one, PP. Physics in the first draw would be 2 by 5. I come to this state. 1 by 4. 1 by 4. Physics in the second draw would be 1 by 4. Which is 1 by 10. So these are the a priori probabilities for the first 2 draws. Each one of them is a cause for the third draw. Each one of them could be a possible cause for the third draw. The third draw is a maths book is drawn, isn't it? Or a maths or a physics book? In the third draw, a maths book is drawn. In the third draw, a maths book is drawn. Yes or no? Right? Probability of drawing a maths book in the third draw. In the third draw. Right? Now, maths and then maths. If it's again maths, then it will become 2 more maths books will get added. So this will be like 7 maths and 2 physics. Now, so after first 2 drawing, this is the state. This is the state for this one, right? Now the probability of drawing a maths book is going to be 7 by 9. 7 by 9. Given this being the cause, that means here to here and here to here. Now the third draw, probability of drawing a maths book is going to be 7 by 9. Yes or no? So that's 7 by 9. If this was the cause, then the probability of getting a maths book in the third draw would be 7 by 9. Right? Now, maths physics. So this was maths, right? And in this, I draw a physics book. I draw a physics book from here, maths and then physics. If I draw a physics book from here, what am I left with? 5 maths and 1 physics. 5 maths and 1 physics. Now, now the probability of drawing a maths book is going to be what? 5 by 6? Is going to be 5 by 6? So that's this third draw, 5 by 6. Yes or no? Physics and then maths. Physics. And then a maths book was drawn. Physics and then a maths book was drawn. Then this would be like 5 maths and 1 physics. Now the probability of drawing a maths book in the third draw is going to be 5 by 6. Now the probability of drawing a maths book in the third draw is going to be 5 by 6. So that's going to be 5 by 6. Physics, maths. Yes or no? Now physics and physics. Right. This was physics, and in the second draw, another physics book was drawn. So I'm left with only maths book because the physics books are not replaced. Now the probability of drawing a maths book would be 1. Right? That's a These are a priori probabilities. This is the probability of the event of drawing a maths book in the third draw for each of these causes. Now what am I trying to find? I'm trying to find that if finally a maths book was drawn, that means this was the event in the third draw, what was the possibility that this was the cause? That means the first two draws were physics. All that I need to do is 1 into 1 by 10 divided by 1 into 1 by 10 plus 5 by 6 into 3 by 10 plus 5 by 6 into 6 by 35 plus 7 by 9 into 3 by 7. That's the required probability. That's the required probability of getting a maths book, probability of getting a maths book in the third draw. Yes or no? Sorry, that was the probability of physics books being drawn in the first two draws. Physics books being drawn in the first two draws, given that the third draw was a maths book. Inverse probability. That's inverse probability. Actually, conditional probability, as simple as this. Right? So if you just, put down things column wise, things will become very simple. If I want to find the probability of this being the cause, then that's going to be this into this divided by this denominator. If I want to find the probability that the first two draws were maths and physics, then the probability was 5 by 6 into 6 by 35 divided by same denominator, and so on and so forth. Do you realize inverse probability is so simple? Yes or no? Stand by. Look at problem number 9. Look at problem number 9. A pair of dice is rolled until a sum of 4 or 6 appears. I have two dice, D1 and D2. These are two dice, D1 and D2, and they are simultaneously rolled, right? Each time they are rolled, there is an X that appears on die D1 and Y that appears on dice D2. Now when X plus Y becomes 4 or 6, then they stop rolling the dice. Right? Now, we want to find the probability that a sum of 6 occurs before 4. That means the rolling terminates without a sum 4 ever occurring. We want to find the probability that a sum 4 or 6, we want to find the probability that sum 6 appears before 4. A sum 6 appears before 4 appears. Now, let me first find out the number of ways in which a sum 4 could appear. So I could have had first die giving me 1, second die giving me 3, first die 2, second die 2, 3, 1. Yes or no? There are only 3 ways in which 4 would appear. Now, number of ways in which six appears. Number of ways in which a sum 6 appears. a sum 6 appears. That means S is 6. Okay. I could have had 1, 5, 2, 4, 3, 3, 4, 2, 5, 1. How many ways? 1, 2, 3, 4, 5 ways. 5 ways. Yes or no? Now, total number of pairs that could appear is 36, right? Total number of pairs that could appear when I roll 2 dice is 36, right? Pairs is 6 into 6, which is 36 pairs. 36 such pairs could appear when I roll 2 dice. 36. Now, realize that there are, out of these 36, 8 would be about 4 or 6. 8 would be about 4 or 6. That means 28 would be about neither 4 nor 6. Right? 28 would be about neither 4 nor 6. Isn't it? Out of 36, 3 plus 5, 8 will be the number of ways in which either a 4 or a 6 appears. Therefore, 36 minus 8, which is 28, would be the number of ways in which neither a sum 4 nor a sum 6 appears, right? So, 28 out of 36 in which neither 4 nor 6 appears as a sum. S. Suppose I've rolled it n times, right? Suppose I've rolled it n times. I've rolled the pair of dice n times. And in the nth trial, a sum 6 appears. And in the nth trial, a sum 6 appears. A sum 6 appears. And before that, neither 4 nor 6 appears as a sum. Before that, how many trials were there? N minus 1 times I rolled, right? In n minus 1 trials before that, neither 4 nor 6 appears as a sum. Neither 4 nor 6 appears as a sum. Now, what's the probability P1 of neither 4 nor 6 appearing as a sum? 28 divided by 36. 28 by 36, which is 7 by 9. 7 by 9 is the probability that neither a sum 4 nor a sum 6 appears. Yes or no? Neither a sum 4 nor a sum 6 appears. The probability is 7 by 9. And I want this to happen for the first n minus 1 trials. I want this to happen for the first n minus 1 trials. And in the nth trial, I want 6 to appear. Then 6 would appear first before 4 appears. Yes or no? In the first n minus 1 trials, neither 4 nor 6 appears. And in the nth trial, a 6 appears. Yes or no? And probability that a 6 appears, let me call it P2. Probability that a sum 6 appears is going to be 1 to 5 divided by 36. Probability that a 6 appears is, in a given rollout, is 5 by 36. Probability that a 6 appears as a sum when I roll the pair of dice, right? That means 4 or 6. So these are my trials. T1, rolling 2 dice. T2, Tn minus 1, and Tn. What is it that I want? I want in these n minus 1 trials, neither 4 nor 6 appearing, and in the nth trial, a sum 6 appearing. And do you all understand that these trials are independent trials? The outcome of T2 does not depend on T1. The sum that appears in T2 has nothing to do with what happened in T1 or what would happen to T3. They are all independent trials, right? What am I seeking to obtain? Neither 4 nor 6 in this. That means I want P1 to take place in this. Neither 4 nor 6, right? In each one of these. And I want P2 to take place here. Yes or no? So this is like P1 into P1. Because they are independent, so their probabilities get multiplied. So probability that a sum of 4 or 6 does not appear in T1 and T2 and T3 and Tn is going to be probability that 4 or 6 doesn't appear in T1 into probability that 4 or 6 doesn't appear in T2 into probability that 4 or 6 does not appear in T3. That's all P1, 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 P1. So that makes it P1 to power n minus 1. Right? For the given event to take place, the required probability is going to be P1 to power n minus 1 into P2. Then this event is taking place. Yes or no? And I want 6 to appear, sum 6 to appear in the nth trial. Yes or no? Yes or no? That means the probability is going to be P1 kya tha? 7 by 9, right? 7 by 9 to power n minus 1, which will be like 4 or 6 not appearing in the first n minus 1 trials, and then P2, which is 5 by 36, that means 6 appearing as a sum in the nth trial. 5 by 6, 5 by 36, 5 by 36. Alright, but n could have been 1, n could have been 2, n could have been 3, n could have been infinity. Yes or no? So what I need is actually the required probability is sum of all of this, where n runs from 1 to infinity. N runs from 1 to infinity. Yes or no? Which is an infinite GP series. Yes or no? 5 by 36 will wriggle out. This is a GP series with common ratio 7 by 9. First term 1, number of terms infinity. So 1 by 1 minus 7 by 9. So this is like 5 by 36 into 9 by 2. 5 by 8 is the required probability. 5 by 8 is the required probability. Yes or no? At random, number 7. A 3-digit number is chosen. That means obviously A is not 0, right? A 3-digit number is chosen at random. What is the probability of having digits in increasing order from left to right? We want the digits in increasing order from left to right. When I go from left to right, A less than B less than C is what I should have. Okay? What's the probability of this happening? Clear? First of all, total number of 3-digit numbers, 9 into 10 into 10, right? 9 ways of selecting A, 10 ways of selecting B, 10 ways of selecting C. So these are the 900 3-digit numbers. Now, if you select any 3 numbers x, y, z, there is only one way in which you can arrange them in increasing order A, B, C. So, how many favorable cases? 9C3, isn't it? (9C3) Yes or no? These are the favorable cases. So the required probability is going to be 9C3 divided by 900. Yes or no? That's as simple as this. And why have I excluded 0 here? Look, A cannot be 0 for sure. And if A is not 0, Neither B nor C could have been 0, because if let's say B was 0, then it couldn't have been increasing order. It couldn't have been increasing order, because then A would have been more than B, for example. So A for sure is not 0, and B and C is also not 0. Right? So 9C3 divided by 900. Do you all understand what I'm saying? Right? Now look at number 2. Two dice, D1 and D2 are rolled. Two dice, D1 and D2 are rolled. Find the probability of getting an even number on the first die or a total of 8. We want to find the probability of getting an even number in D1 or a total of 8, or a total of 8. Even number in D1 or a total of 8, we want to find the probability. Do you understand the problem? Find the probability of getting an even number in D1 or a total of 8. So now even number in D1 is like 3 by 6. The required probability is going to be of getting an even number is going to be 3 by 6. Yes or no? There are 3 even numbers of a total 6, so that makes it half. Or sum 8. Or sum 8. Sum 8 means I could have had 2 6, 3 5, 4 4, 5 3, 2 6, 6 2, 1 2 3 4 5. 5 ways, right? So this probability of getting 8, sum equal to 8. So let me call this P1. This is P2. Probability sum equal to 8 is 5 by 36. Total number of ways are 36. 5 are favorable. So probability of getting sum equal to 8 is 5 by 36. Right? Now, what is the probability P3 of sum equal to 8 plus D1 is even? P1 is about getting a sum equal to 8, and D1 is even. So then look at sum equal to 8 and D1 even. This is 3, right? 3 divided by 36 is the probability, right? 3 favorable cases of D1 being even, and the sum being 8. 3 are favorable cases of getting a sum 8 and D1 equal to 8. The favorable cases are 1, 2, 3 out of 36. So 3 by 36. Yes or no? Now principle of inclusion exclusion. Probability of getting sum 8 or even number in D1 is going to be P1 plus P2 minus P3. Yes or no? So now whatever P1 is half, P2 is 5 by 36 minus P3, which is 3 by 36. Now whatever this turns out to be, 1 by 18, 5 by 9. 5 by 9. Yes or no? Shall we move? All's good, right? A and B are any two events. A and B are any two events of a sample space such that PA is 0.3, PB is 0.8, and probability of A intersection B is 0.16. We want to find the probability that exactly one event happens. We want to find the probability that exactly one event happens. That means we want to find the probability of this region. We want to find the probability of this region. Either A or B. Exactly one, either A or B. Now do you realize this region is PA minus P intersection B? This region is PA minus P of A intersection B. So this region is PA, which is 0.3 minus 0.16. Yes or no? Right? This whole thing is 0.3 minus 0.16, which is 0.14, which is 0.14. Now this region is PB minus P of A intersection B, and PB is what? 0.8 minus P of A intersection B is 0.16, which is 0.64. So the required probability would be 0.64 plus 0.14, which is 0.78. 0.64 plus 0.14, which is this plus this, which is 0.78. And do you realize these are mutually exclusive regions? So I can add their probabilities because they are mutually exclusive. 0.78 is the required probability. 0.78 is the required probability.